Welcome to our pre-recorded class session for today. As promised, it's election day, which is now a state holiday in Illinois. So the college is closed, so that's why we're not having class today in person. So if you are eligible to vote in Illinois, make sure you get out and vote today if you haven't done so already. Remember, Illinois is a state where you can register to vote the same day as you vote, so there's still time. So what we're going to do today is just do what we basically do in class, which is run through a few problems from the homework that you all might have struggled with according to my math lab. And then unlike normal where you'd be able to ask me class questions in person, you can feel free to shoot me an email or a remind message if you have questions about anything we go over today, or if there was a problem on the assignment that we didn't go over that you struggled with and would like more clarification on. Also, as always, don't forget that we have a quiz due tomorrow night. So don't forget to take that, even though I'm not there to remind you in person. So let's go and get started. So the first section for this time is section 5.2. So there were quite a few problems. 4.2, sorry. Quite a few problems that everybody kind of struggled with. You guys a lot of you had to redo this first one off the bat, but I think I'll skip that one because probably that was just getting you started. But let's see. There were a couple down here. So here's one. Let's just start with this one at the bottom, where only a third of you got it right, a third of you got it wrong, and a third of you didn't attempt it at all. So that seems like a good one for us to go over together. Okay, so it says find the function with the given derivative whose graph passes through the point P. Okay, so we've got the function r prime of theta equals 3 plus secant squared theta with the point P of pi over 4 comma negative 1. Okay, so let's give that a go. So the idea here, remember, is we basically want to ask ourselves, what function we're working backwards here. So what function has the derivative that's given? Okay, so for example, if we start with this first one, start with the first piece here, we want to ask ourselves, what function has the derivative 3, right? And something that would have a derivative 3 would be 3 times a variable. So this would just be r then of theta. Well, for that would be 3 times the variable, so 3 theta. Okay. Then what function has the derivative secant squared theta? Well, that's just tangent theta. Okay. And then the problem we run into here is with derivatives, we lose the constant, right? Because what has a derivative of 0? Well, a constant. Okay, and that's where this point comes in. Because here's the derivative, the original function. It could be anything that is 3 theta plus tan theta plus some constant. And so to figure out what that constant is, we're going to use this point that we've been given. So we're going to substitute those in. So r theta is negative 1, and theta is pi over 4. And then we're just going to solve for our constant here. Okay. Let me make sure I typed everything right. Yep. Okay. So that'll be negative 1 equals 3 pi over 4 plus the tangent of pi over 4 is 1 plus c. Okay. And then we could combine like terms. Well, let's just bring everything over here. So this will be subtract 1 from both sides, subtract 3 pi over 4 from both sides. And so we get negative 3 pi over 4 minus 2 equals c. So our function, r theta, should be 3 theta plus tan theta minus 3 pi over 4 minus 2. So let's try that. So 3 theta. There's a way for me to... Yep, there it goes, like that. Plus tan theta. Yeah, I have to use. Minus 3 pi divided by 4 minus 2. And that's the idea there. So that's how that one worked out. Okay, so we're just working backwards to do problems like these. Okay. So let's go ahead and just look at another one of these. That's the same idea as the one we just did, but a different function. So here's another one. So here's the derivative. Find the function given this derivative and this point. So let's give that a try. So this one, our derivative f prime of x equals 2x minus 3 with the point -5 comma -1. Okay. So then we're going to try and write our f of x, right? So what has a derivative of 2x squared? I mean 2x. Well, we know it's going to have an x squared, right? Okay. Right? Because when you take the derivative of x to a power, it just goes down by 1. So if the derivative has x to the first power, the original function has to have x squared. And then we can just check, does this x squared give us our 2x? Yeah, the derivative of x squared is 2x, so it'll just be x squared. Then we've got our -3. Well, that'll be -3x, right? Because the derivative of -3x is -3. And then we have to have some constant, once again. Because if there was a constant out here, it would just go away when you take the derivative. Because the derivative of a constant is 0. Okay, so now we can plug in our point. So this will be -1 equals -5 squared minus 3 times -5 plus the constant, and just solve for c. So this would be -1 equals 25 plus 15 plus c. -1 equals 40 plus c. Subtract 40 from both sides, and we get -41 equals c. So this would be f of x is x squared minus 3x minus 41. Okay, so x squared minus 3x minus 41. Okay, so good job. So that's the idea of how you do problems like that. So those were the problems at the end of this homework assignment, where you're given a derivative and a point, and you have to find the function. So now let's go back a little bit, and let's look at a different type of problem, now that we've talked about that type. Let's see what this one is. Okay, so this is just same idea, just 3 different options, 3 different problems. So you'd have to do f prime of x equals 2x, what's f of x, and then find the function and then plug in 1 for each of those. So same idea as what we just did. Okay, this will be a good one to do. So this one says, show that the function r of theta equals secant theta over 1 minus 1 over theta cubed plus 5 has exactly 1, 0 in the interval 0, comma pi over 2. And it's going to walk us through that. So Rolle's theorem states that for a function f of x that is continuous at every point over the closed interval a comma b and differentiable at every point of its interior a comma b, if f of a equals f of b, then there is at least one number c in a comma b where f prime of c equals 0. Okay, so let's go on to the next step. Whoops, I hit the wrong button. That's not what I wanted. Okay, so it says find the derivative. I want you to start out by finding the derivative of this. Okay, so we've got r of theta equals secant theta minus 1 over theta cubed plus 5. Okay, so we want to find that derivative. So r prime of theta, the derivative of secant theta is secant theta tan theta. The derivative of 1 over theta to the fourth is positive 3, 1 over theta, or let me write that a better way, is positive 3 over theta to the fourth, right? Because when we have a exponent in the denominator, we multiply by the opposite, which is why negative 1 times negative 3 is positive 3, and we add 1 to the exponent, and the derivative of 5 is 0. Okay, so that's our step 1. So plug that in here. So secant theta tan theta plus 3 divided by theta to the fourth. Okay, so that was step 1. Can the derivative of r theta be 0 in the interval 0 comma pi over 2? Okay, so one way to check that, and probably the easiest way to check that, is to graph it. Okay, so I'm just going to come in here and I'm going to graph y equals secant x tan x. Oops, sorry, I'm screwing that up. Secant x tan x plus 3 divided by x to the fourth. Okay, and then we just want to look at the interval from 0 to pi over 2. So we can look here. Here's 0. And then pi over 2 is, let's just type it in here so we can see it. Pi over 2 is 1.57. So is it between 0 and 1.57, which is about right here? Is this equal to 0? Is the derivative equal to 0? And the answer to that's no. Okay, right, because we can see that. Okay. So according to Rolle's theorem, since the derivative of r theta is never 0 in the interval 0 to pi over 2, there cannot be 2 points, theta equals a and theta equals b, for which r of a and r of b in this interval. In other words, the function r theta has at most 1 0 in the interval, because we can because it's never 0, we can't have 2 points where theta is a and theta is b, we get the same y value. And in order to have 2 zeros or more, we'd have to have RA and RB both equal 0, right? We'd have to have 2 different points where R of the first point and R of the second point are both 0. And since we don't have that, because the derivative is never 0, which means the slope of the graph is always either increasing or decreasing on our interval, we can have at most 1 0. It can cross that at least once. So then, which theorem can be used to determine whether a function has any zeros in a given interval? And the answer to that, if I'm remembering correctly, is the intermediate value theorem. Okay, because the intermediate value theorem tells us that if we have 2 values, if we find 2 y values on a continuous function, then all the y values in between those have to exist on the interval between those 2 values. So like, for example, if I look at the graph here of what we just drew, if I pick a y value here, a point here that has this y value, and then I pick a point over here that has this y value, all the y values between it have to occur if the graph is continuous. So between those 2 points, I have to get all the y values in between. That's the intermediate value theorem. So to apply this theorem, evaluate the function r theta equals secant theta minus 1 over secant cubed theta plus 5 at each endpoint of this interval. Okay, so plug these 2 values in. Okay. And it wants us to round, so I'm just going to type this in to the calculator. Is going to be the easiest way to do that. So, let's see. So it's secant of pi divided by 8 minus 1 divided by pi divided by 8 to the third plus 5. Okay, and I'll type the answers here in a minute, but first one, we get negative 10.43, and then we're going to do the same thing for pi over 4. So for the first one, we get negative 10.43. Okay, and for the second one, we get 4.35. Okay, and so now, because the intermediate value theorem, these two values, one is positive and one is negative, we know that there is exactly, according to the intermediate value theorem, there is at least one 0 in that interval, right? The intermediate value theorem by itself tells us that there's at least one, that we cross 0 at least once. Okay, and now if we put those two things together, if r theta has at least one 0 in this interval, and this interval is fully contained in our original interval, then r theta has at least one 0 in 0 to pi over 2. So there's at least one 0 in 0 to pi over 2. If you put those two things together, that there's at least one 0 in there, and Rawls' theorem says that there's at most one 0, that gives us that there's exactly one 0. And so that's the idea behind that problem. Okay, so that's using the intermediate value theorem and Rawls' theorem. Okay, so that's it. All we're going to go over in 4.2. So now let's skip ahead to the next section and look at a couple problems, at least from 4.3. Okay. Okay, so let's start with this one. So, good number of you only got partial credit for this who didn't quite get this one right. So let's go ahead and look at this one. So it says, find the open intervals on which the function is shown in the graph is increasing and decreasing. Identify the function's local and absolute maximum and minimums. Okay, so this one's just looking at a graph. So we can talk, this is a good way to talk about these problems. So it's actually would be almost easier to find the maximum and the minimums first, and then talk about increasing and decreasing. But what you can see from the graph here is from negative 20 to negative 10, we go up. Then from negative 10 to 0, we go down. Then from 0 to 10, we go back up. And then from 10 to 20, we go back down. So this function goes up, increases from negative 20 to negative 10. And notice I'm using parentheses. I know to use parentheses because it's asking for open intervals. Open intervals are ones with parentheses. And then it also goes up from 0 to 10. Right? So this interval is negative 20 to negative 10, and this one is 0 to 10. Notice I'm only including the x values. So we say on which x values are the y's going up or down. Okay, so that's where it's increasing. And on which open intervals is it decreasing? Well, it goes down from negative 10 to 0, and then from 10 to 20. Basically, on the other parts of this function, it's decreasing. Okay, so that's decreasing. And it says, if the function has an absolute maximum, where does it occur? Well, so where is its absolute maximum point? Well, that's up here. Well, the highest the graph goes is up here. So that's its absolute maximum, is at negative 10, comma, 15, right? The y value here would be 15. And then it says, are there any local maximums? So are there any points where it's bigger than all the points around it? So other points where it's bigger than the points around it would be this point right here, right? At 10, comma, 0. It's not bigger than the rest of the graph, but it's bigger than the points on its left and its right. So that's a local maximum. Okay, and then it's asking me what is the absolute minimum. So what's the lowest this graph ever goes? Well, that's over here at this point on the right. So that's at 20, negative 10. Okay, and then it's going to ask me for local minimum. Are there any local minimum? And so if we look here, this point at 0, negative 5 is lower than the points around it, and so is negative 20, 5, right? It's lower than the points on its right. And we only have to worry about on its right because it's an endpoint. So we've got 0, negative 5 is a local minimum, and so is negative 20, 5. Okay, and so that's the idea about local minimum and local max. So that's all looking at a graph. And a graph can be a great tool to help you do these problems. So don't be afraid to graph these if you feel like you're getting stuck. Okay. So let's just look at the first problem from this assignment real quick. Okay, so here's an example where they're giving us the derivative and they're asking us to find the critical points and so on. So remember, critical points are simply places where the derivative equals 0 or it's infinite. So in this case, we've got f prime of x equals x times x minus 2. So the critical points are going to be where that equals 0. So x equals 0 and x equals 2, right? Both of those would make this function equal to 0. So the critical points are at x equals 0 and x equals 2. Then it says, find on what open intervals f is increasing and on which intervals it's decreasing, if there are ones. So to find that, what we have to do is remember, so this is good stuff, when f prime of x is positive, the graph is increasing. When f prime of x is negative, it's decreasing. And so with these places that's 0, it basically gives us 3 intervals. This breaks the number line up into 3 intervals, right? We've got this stuff over here in the middle and over here. So we've got negative infinity to 0, 0 to 2, and 2 to infinity. And so the question is just, are we increasing or decreasing on each of those intervals? And a really easy way to do that, to figure that out, is just plug in a value to the derivative that's in that interval. So like, for example, I could plug negative 1 is in this first interval, so I could plug it into f prime. So that would be negative 1 times negative 1 minus 2, which is negative 1 times negative 3, which is 3. So that's going to be positive, so this is increasing. And then we could do the same thing for these other two. So 1 is in this middle interval, so 1 times 1 minus 2. So that's 1 times negative 1, which is negative 1. That's a negative number, so this one's decreasing. And then for the last one, we could do, let's say, 3. But you could pick any number bigger than 2. So 3 times 3 minus 2 is 3 times 1, which is 3. So that's positive, so that's increasing. So based on that, we know that the function is increasing on the intervals negative, infinity, comma, 0, and 2 to infinity, and that it's decreasing on the interval 0, 2. So in this example, they're asking you to do the same things they're asking you to do in a lot of these questions. They're just asking you to do it from the derivative. So you have to use the algebra skills. You can't necessarily just look at the graph, although you could look at the graph to find the values we just found. Okay, so that's the idea of this section. So let's go down here and do one closer to the bottom. So let's look at this one, because only 2 of you got this one 100% correct. Okay, so this one says, find the open intervals on which the function is increasing and decreasing. Identifying the function's local and absolute extreme values, if any, saying when they occur. Okay, so the function is g of x equals x times the square root of 18 minus x squared. So one option for this is to start out by looking at a graph of it and see what this looks like, so we can see what we're dealing with. Okay, so y equals x times the square root of 18 minus x squared. Okay, and so this gives a fairly good picture of what this looks like. So you can tell from this that there are going to be some extreme values, local extremes, most likely. I can actually tell you this graph's slightly inaccurate, but because this is not working out quite right. But you can see, well, here, these are actually pretty good now. We can see here, yeah, these are not giving me great values. Let's try graphing this in GeoGebra. I don't know why that one's not really working. I thought I had done the thing that would make that graph it right, but let's try graphing this in GeoGebra. Okay. So yeah, so it looks basically the same as the graph we just did. The values are just going to be better here. Okay. And so, but we can see it stops here. We do have a local minimum. We have an absolute minimum over here. We have an absolute maximum over here. And then the endpoints are going to be local mids and local maximums. And so we could find those values algebraically, right? So the way we do that is we'd have to use the product rule here and the quotient and the chain rule. So let's start with the product rule, right? So u is x and v is the square root of 18 minus x squared. So u prime is 1 and v prime is 1 over 2 times the square root of 18 minus x squared times the derivative of 18 minus x squared. The derivative of 18 minus x squared is just negative 2x. Multiply these together, the 2's cancel, and we get v prime is the opposite of x over the square root of 18 minus x squared. Okay, and now g prime of x is going to be u times v prime plus u prime times v. So g prime of x is x times negative x over the square root of 18 minus x squared plus 1 times the square root of 18 minus x squared. And then we're going to simplify. So g prime of x is negative x squared over 18, the square root of 18 minus x squared plus the square root of 18 minus x squared. We need to get a common denominator. So multiply by the square root of 18 minus x squared over the square root of 18 minus x squared. So g prime of x is negative x squared or the square root of 18 minus x squared plus 18 minus x squared over the square root of 18 minus x squared, which is g prime of x equals 18 minus 2x squared over the square root of 18 minus x squared. Okay, so now what can we do with that? So now we want to know when that is equal to 0. And also when is it undefined. So we can start by dealing with when this thing will be equal to 0. Okay, so it'll be equal to 0, and I'm running it when the top equals 0. Okay, so we can solve that pretty quickly. Negative 2x squared equals negative 18. Divide both sides by negative 2. You get x squared equals 9. So x equals plus or minus 3. Okay, so we're going to get critical values at 3 and negative 3, which we can see right here, negative 3 and 3. We can see that in the graph. So that matches up to what we're seeing in the graph. And then we want to know, when is this thing undefined? Well, it's undefined when 18 minus x squared is defined when 18 minus x squared is greater than 0. Okay, and that's going to be the case when x, right, 18 minus x squared. So that means that that's going to be the case when 18 is greater than or equal to x squared. So we're going to get a plus or minus here. So basically what needs to happen is x has to be between the negative square root of 18 and the positive square root of 18, which is out of room on the bottom, so I'm going to write above. Negative 3 root 2 is less than or equal to x, which is less than or equal to 3 root 2. So it has to be between those two numbers. And that's also what we can see in the graph, right, is the function stops at those two values over there. So let's start trying to put in some answers here. Okay, so the function is increasing on the open intervals, and we can see on here that the graph increases from negative 3 to 3, right, on this piece in the middle, and then it's decreasing on the other two. So it increases from negative 3 to 3. And then the function is decreasing on those other. Now, it wants you to type exact answers in simplified form, so that's where these come in. So the far left-hand endpoint is this negative 3 root 2, and we go until we get to negative 3. So it's going to decrease from negative 3 square root of 2. Sorry, I'm trying to use some shortcuts, and right now I don't. To negative 3. And then it also decreases from 3 to 3 square root of 2. Okay. And then it says find each local maximum, if there are any, and select the correct choices. So like we said in the graph, there are local maximums. They're here and here. Here and here. Okay, so we just need to plug in these values into the original function. So the function has a local maximum at two values of x. In increasing order of x value, they are g of negative 3 square root of 2. And if you plug that in, you get 0. And they're also at 3. And if you plug that into the original function, you get you get 3 times the square root of 2, I'm pretty sure. No, you don't. You get 9. If you plug in 3, you get 9. Okay, so those are the local maximums. And then from the graph, we can see that there are local minimums down here at this point and at this endpoint. So that's at negative 3 and at 3 root 2. So there's going to be local minimums at negative 3 and at 3 square root of 2. And then once again, you just have to plug these values in. So if you plug in negative 3, you get negative 9. And if you plug in 3 root 2, you get 0. And then if the value has any extreme values, which extreme values, if any, are absolute. So we do have an absolute maximum up here and an absolute minimum down here. Those are the highest and lowest points. So it has an absolute maximum and an absolute minimum. The absolute maximum value is 9 at positive 3, and the absolute minimum is negative 9 at negative 3. Okay? And so that's how you would do one of these problems, and that's what all the other problems in this section are about. But that's about as difficult of a function as I'm going to ask you to do this with. Okay, so that's about all the time I want to take on this for today. Thanks so much for being with me during this pre-recorded session. Just one other reminder besides the ones I said at the beginning of class about doing the quiz and things like that. I am going on paternity leave soon. Mr. Sanchez will be taking over my class. My planned date for that to happen is next Wednesday, so a week from Wednesday is when I plan to start my leave. And so if you have any questions before that date, you can email me, contact me by Remind. If you have any questions after that date, you'll need to contact him. I'll be putting his contact information on the course homepage. And so I will be in class hopefully next Tuesday. And then after that, good luck with the rest of the semester. And hopefully we'll see you all again sometime.